For this video, we're going to be looking at the M&M data again that we did for chapter 14, but now we're going to try to test to see if customers are being shortchanged, because according to the company that makes them, the average number of M&Ms that come in these fun-sized bags should be about 15. Question 1 wants to know then, what are the parameter of interest and the hypotheses? Our variable that we're collecting from each bag is the number of M&Ms in it, which is a quantitative variable, which means then that our parameter is going to be a mean. Quantitative variables summarized by averages. Our population mean is denoted by the letter mu, and we don't know what the population mean is exactly, at least what the number is, but we can write it out in words. Mu is going to be the average number of M&Ms in all fun-sized bags. That's what we want to try to learn about. While we'll never be able to know it, we can try to create some ideas about it. And according to Mars, they state that the average number per bag is 15. And without any evidence otherwise, we'll believe them. Our default belief about these fun-sized bags is that the average number contained within each one is 15. So for our null hypothesis, we'll take the parameter of interest, mu, and set it equal to what the company states, 15. So this mean goes here. And then we'll do the same thing for the alternative hypothesis. Same parameter, mu, same number, 15, those don't change. What sign goes in the middle is going to depend on the question we're trying to answer. We want to determine if customers are being shortchanged, meaning that the average is less than the 15 that they advertise. So we're just going to change this equal to sign to a less than sign. And like what we saw in the previous sheet, the hypotheses are about parameters, they're not about the statistics, so you'll never see a Y bar here. That's going to be our cardinal sin for hypothesis tests. If you put a statistic in for your null, it's automatically wrong and you don't receive any partial credit. So step 1 of a hypothesis test down. What are we trying to determine? Step 2 is we want to check our conditions, so that way we can actually find a p-value. First condition that we need is a random sample. The M&Ms that we opened up don't really constitute a random sample since they all came from the same large bag. So that means that we don't have a random sample of all M&Ms. If the machine was malfunctioning at a certain time point, most of those fun-sized bags are going to come from when the machine was malfunctioning. So not a truly random sample. Our sample size is 145. And what we need to make sure is our sample size isn't too big, that N is less than 10% of the overall population. I don't know how many fun-sized bags of M&Ms have ever been made. I can probably assume that it's more than 10 times my sample. 10 times 145 gives you 1,450. Probably more than 1,450 fun-sized bags of M&Ms have been made. We can check that condition off. And then the last one is we just need to make sure we have a sufficient sample size. We either need our sample size to be greater than or equal to 40, or for the sample data to be bell-shaped. We have a sample of 145, which is greater than 40, which means then we meet our condition. So we have 2 of the 3. We don't have a random sample, but as long as we believe that that bag is somewhat representative of all M&Ms, we're probably okay. Anytime we're working with means, once we check our assumptions, we can create a model. When we're working with means, we're always going to use a t-distribution. What's unique about t's is they need degrees of freedom, and we'll say our degrees of freedom for a one sample test is just going to be our sample size minus 1. So our degrees of freedom are n minus 1, or 145 minus 1, which is 144. The next thing we need to do then is calculate our test statistic. In order to get a test statistic, we need our sample statistics. So we need our sample mean of 15.1 and our sample standard deviation of 1.65. And we get those numbers from the data. We have 145 bags that people have opened up. We calculate the mean and the standard deviation. And according to StatCrunch, our standard error should be about 0.137. So the statistics and something like a quiz or an exam I would just give you, but here, since we have the data, we can use StatCrunch to calculate it. Well then, what we can do is find our standard error. The standard error for a sample mean is fairly straightforward. You take the sample standard deviation. We want to replace deviation with error. We do that by dividing by the square root of our sample size. So we'll take how much the individual bags vary from one another. the sample standard deviation, divide by the square root of 145, and rounding off to 3 decimal places, we get 0.137. And then the next thing we can do is calculate our test statistic. And the way all test statistics work is they are going to be your sample statistic minus the value in the null hypothesis divided by that statistic's standard error. Every single test statistic we see in this class will follow this basic formula. In our case, our sample statistic is y bar, the value in the null hypothesis is mu0, and our standard error we can find from the formula up here. And the basic idea behind a hypothesis test is what we're doing is we want to take what we observe. We observed a sample mean of 15.1 and compare it to what our default assumption says we should get. According to the null hypothesis, we should expect to get 15 M&Ms on average. I want to know how different these two numbers are, how far apart they are. Well, straightforward, you just take 15.1 minus 15 and you get 0.1. But in statistics, to determine how far apart two numbers are, you want to calculate a z-score. And now that we're using a t-distribution, we'll replace z with t, but essentially it's still a z-score. So we'll take 15.1, subtract 15, divide by its standard error of 0.137, and if you do that, we end up with a test statistic of 0.73. You want to remember that these test statistics can be used to determine if our sample is unusual. If you get a test statistic above +2 or below -2, usually indicates an unusual sample. A test statistic between -1 and +1 indicates what we saw would be really common if the null hypothesis were true. So if Mars isn't lying, our sample average of 15.1, since our test statistics between -1 and 1, would be a typical sample we could reasonably expect to get. Meaning, our p-value should end up being fairly large. The p-value measures how usual the sample is. The larger the p-value, the more common our sample. The smaller the p-value, the more unusual the sample. So that's step 3, is you want to calculate your test statistic. Step 4 is you want to find the p-value. To calculate a p-value, you need two things. You need a test statistic, and you need a theoretical distribution. And we have both of those. Step 3, we found our test statistic. Step 2, we found our probability distribution. That's going to be a t with 144 degrees of freedom. We want to draw our t-distribution out and shade the area that we're looking for. So we have our t. T's are centered at 0. They're symmetric, just like a normal is. We found our test statistic to be 0.730, so that's fairly close to 0. So we'll have a line here of our test statistic of 0.730. And we want to figure out if we want the area above, below, or both tails of this t-distribution. To find the test statistic, you use the null hypothesis. To find the p-value, we use the test statistic and the alternative hypothesis. So if we scroll back up, we want to see if our mean is less than 15. This less than, you can kind of treat as an arrow that's pointing to the left. So we want everything at our test statistic in less than it. So we'll shade this entire area. So that would end up being our p-value. To find a p-value, you're always going to use a CDF. So our p-value will be t-CDF. We start shading at some large negative number. We stop shading at our test statistic. And our degrees of freedom are 144. If you put those into a calculator, so we'll go to second vars. This time we want t-CDF, which is option 6. Lower bound of a large negative number. Upper bound of 0.730. Comma, degrees of freedom of 144. We hit enter, and we end with a p-value of 0.767, which would mean if Mars is telling the truth that the average number of M&Ms you get in a bag is 15, the probability of getting a sample mean of 15.1 or smaller would happen about 77% of the time. Or about 3 in 4 samples would give us our sample mean or something smaller. We say smaller because the alternative is less than. So something that occurs 3 in 4 times isn't unusual at all. So since we have a large p-value, our sample is typical, we fail to reject our null hypothesis. That's our generic conclusion. And then our conclusion in context. is that we don't have evidence to conclude that the average number of M&Ms that come in a fun-sized bag is less than 15. So your conclusion in context is going to take the alternative hypothesis, and the alternative hypothesis says the average is less than 15. And either we have strong evidence for the alternative if we reject the null hypothesis, and we don't have strong evidence for the alternative if we fail to reject the null hypothesis. Since we failed, that means we don't have strong evidence. If we didn't fail, we'd replace this with we have strong evidence that whatever the alternative hypothesis says. So if I wanted to lodge a complaint against Mars saying that they have false advertising for the number of M&Ms that come in a bag, I don't have compelling evidence for that, and I likely wouldn't have a lawsuit make it to court at all based off the evidence that we've gathered. For a little added bonus, let's go through the same steps, but see what our hypothesis test would be if we want to determine if what Mars is saying is true, that the average number of M&Ms in a bag is 15. So our null hypothesis, still about the population mean mu, we'll say that's equal to 15. And if I just want to see, are they telling the truth? Maybe the mean is more, maybe the mean is less, but if it's anything other than 15, what they state isn't correct. So we'll say our alternative hypothesis then is just that mu is not equal to 15. I don't know if it's more or less than, just I want to see, is it different? We can check our conditions. If all you do is change what your alternative hypothesis is, the conditions stay the same. So if we met them earlier, we meet them now. Still don't have a random sample. Sample is less than 10%, and we have a sample size larger than 40. So we still meet all our conditions. We want to calculate our test statistic. Our test statistic's still going to be a t because we're working with means. Still our sample mean minus the value in the null hypothesis over the standard error. Well, our sample mean is still 15.1. Our value in the null hypothesis is still 15. Our standard error, S and N, stay the same, so that's still 0.137, which means just changing the sign in your alternative doesn't affect your test statistic, because we said the test statistic just depends on the data and the null hypothesis, not the alternative at all. So this will still end up giving us a test statistic of 0.730. But changing the alternative hypothesis will affect the p-value. If we draw out the t-distribution again, if we draw out our t-distribution, it would look something like this. Still centered at 0. We'd mark where our test statistic falls of 0.730. So far, nothing has changed. But where it is going to change is which part of this curve that I want. Since it's not equal to means we want a 2-tailed test, not equal to and 2. So it means we want the area above. We'll change this from positive to negative. You just swap the sign. So it'll be a negative t up down here. So negative 0.730. And now we want the lower tail. I want to figure out what this area is, this area, and combine them together. And that will give us our p-value. The good news is that, just like a normal, t's are symmetric, so we can just do tCDF, find out what our p-value is. So 0.730, some large positive number, our degrees of freedom of 144, and then we just want to multiply this by 2, so that way we get both tails. Back to our calculator, we go to second vars, tCDF is option 6, we start at 0.730. We stop at some large positive number. Our degrees of freedom are 144. That will give us this upper part. We need to multiply it by 2 to make it a 2-tailed test. And we end with a p-value of about 0.467. Still not a small p-value. Basically, our sample, your chances of getting a sample mean 0.1 or more away from 15, so basically 15.1 or higher or 14.9 or lower, would happen about half the time. Half the time, so our sample isn't unusual, not an unusual sample, can't reject our null hypothesis. So there's no evidence that Mars isn't telling the truth, that the population mean for the number of M&Ms in a fun-sized bag, we have no evidence that it's different than 15.